Hi, so my name is Vasily Korabel. I'm from same institute, Danish Meteorological Institute in Copenhagen, and I will present the use case of improving the Copernicus Marine Service SST and other variables by assimilating the satellite system. And for those who are not familiar, what is the MFC is? It's a monitoring and focusing center. The global ocean is divided into the regions. The global ocean is modeled by the Mercator Ocean International, and there are several regional centers that run the regional models. For example, Arctic is run in Norway. Northwest Shelf is run in UK. Now it's moving to Germany. And by coincidence, we were chosen to run the Baltic Sea. That was fortunate. So we are developing. Yes. I think let's skip one slide. Okay. Our MFC produces both near real-time products and the reanalysis. And we are several institutes, so we split the tasks. Right now, the operational center is located in Sweden, and it produces the daily forecasts of physics, biogeochemical variables, and the wave. The wave is actually run in Finland. And we are responsible for the multi-year products of physics and biogeochemistry. I should mention that out of those products, then we can derive the marine ocean indicators, such as the marine heat waves, and all of these products you can find on the Copernicus website catalogs. Different slides. Okay. So this is their schematic of their both near real-time and multi-year production systems. And we really emphasize that we are trying to harmonize both systems. So for the user, the only difference between near real-time and multi-year reanalysis would be the atmospheric forcing. For the near real-time system, it comes from the operational atmospheric model. For the reanalysis system, it comes from the RF5 and the boundary conditions that, in our case, it comes from the Northwest Shelf reanalysis, and for the near real-time system, it comes from the Northwest Shelf near real-time system. The modeling components, data assimilation components are identical in both systems. So here's the area that we modeled, and in red box, you can see that our product area. So in reality, we have a larger domain that because we have to get the inflows into the Baltic Sea or the salt water from the North Sea. And we behind our physical component, we have the NEMA model, which is right now it's NEMA 4.0. We are upgrading it constantly, so it's going to be NEMA 4.2. When we run at very high horizontal resolution at 1 nautical mile, which is about 2.5 kilometers, with 56 vertical layers. And we produce in Copenhagen, we produce a reanalysis from 93 to 2023 right now. And we assimilate basically everything we can get. So we simulate for the in situ, we assimilate temperatures or salinity profiles, coming from CMEMS catalogs, from ICES, from Shark database, which includes, in recent years, we include also Argos and floats, and we also simulate the biogeochemical profiles, with, for example, oxygen, nitrogen, phosphate, and we simulate also ice charts, and that helps to improve the physics a lot. For example, you can see that compared to the previous reanalysis that we had before, we greatly reduced the deep biases in the system. So we tracking the observations a lot more closely, which is the key for biogeochemical variables as well. So we better model biogeochemistry because of the improved physics. And in terms of satellite, we assimilate level 3S products from the Copernicus catalog, and the near real-time system assimilates, obviously, near real-time products, while the reanalysis assimilates the reprocessed level 3S product. And why do we need to assimilate anything at all? It's because the models, when they run freely, they obviously have errors, which has to be corrected. For example, the Baltic Sea model that we have exhibits the negative bias in SST in winter, which means that the model is cooler than the observations. And in summer, we have both positive bias in the North Sea and light negative bias in the Baltic Sea. So we have to reduce those biases, and that's why we simulate their satellite products. But we came with a surprise that when we assimilate level 3S into the near real-time system, we found that the model, compared to the observations that we assimilate, exhibits positive bias now. And that was a little unexpected. So we checked how this compares to the reprocessed level 3S. And it turned out that the bias features are different. This is the monthly mean for May 2023. And the reason why is because the near real-time product and the reprocessed product happen to be offset by approximately 0.4 kelvins, which is quite big. It's on the order of our model error running freely. So we really have to be careful what we assimilate and what we are comparing to. So that was one unexpected prize that we got. But as I said, our center in Copenhagen produces the multi-year product, and we assimilate the reprocessed product. And how can we check the results? We compare against the level 4, which is also produced in Denmark, in our institute. So the level 4 is produced out of level 3S. So it's not quite independent, but it provides the like first-hand results, and we can check that the model bias is still there. We reducing the biases, but it still has a seasonal SST bias, which is much smaller than in the free model. The root mean square error is generally small, below 0.6 kelvins, and the standard deviation of the temperature is consistent with observations, which is very important. But we can also compare to the in situ observations, which we haven't assimilated, and those are the coastal stations. So I should emphasize that those observations were not assimilated and comes from the independent data set. And we can see that overall we have a slight negative bias consistent with the satellite SSTs. The root mean square error is below 0.7, and normally the correlation scores are like around 0.7, 0.8, which are quite good. So when we assimilating the level 3S and comparing to level 4, what we are looking for in the products is obviously the low errors, spatial and time consistency, but also how the products represent the sharp gradients. For example, fronts of the SST, which you can see that this is the winter in Kattegat. There is a sharp front of the SST. And on the top left, you can see that the level 3S product observes this area quite poorly because of the cloud cover and also presence of ice. The level 4 product, it's a gap-free. It has gaps where there is ice, but otherwise it gets this front quite okay, but compared to the model, it looks very smooth. So the reprocessed, the reanalysis on the bottom right shows that this front is much more variable. It has more meandering features and eddies developing. So the level 4 is a good product, but it's very smooth. So which might, yeah, we cannot assimilate level 4. Therefore, we have to still assimilate level 3 products. So what can we compare our SSTs against? We have another centers producing the level 4 SSTs. For example, the Ostia analysis, which is also level 4 at comparable resolution, 0.05. And in addition to assimilating the satellite sources from multiple satellites, it it assimilates the in situ and ice charts. And it also has the advanced data simulation scheme. So it uses the NEMO-VAR, the 40-VAR system, and it has this NEMO-VAR error covariances, which helps a bit to improve the spatial scales. So if we compare our reanalysis to the Ostia and to the level 4, you can't say which product is better. So, both, especially monthly mean maps or seasonal mean maps compared to the error standard deviation, which is quite similar. But if we have a look at the spatial gradients of the SSTs, on the left, you can see the spatial gradients of the level 4 from BMI, and it has a gradients which are a good magnitude, but they are very spatially uniform, which was a bit unexpected. The Ostia gradients in the middle, they are quite consistent, what we expect, where they should be, but the magnitude of those gradients are quite low. And our reanalysis on the far right has gradients which are right magnitudes and in the right locations where they should be. So I think that brings me to the conclusion that both near real-time systems and multi-year system benefit from SST assimilation. You just have to be careful what to compare with. Level 4 SSTs provide very good insights with no gaps and good time consistency, but there are challenges in reproducing SST fronts, positioning of eddies and upwelling regions. And reanalysis offers the alternative view to the level 4, providing the gap-free SSTs consistent with the other variables, for example, sea level and currents. And it's worth looking at alongside with the level 4 system. So I think that. Okay.